PE. Today we are going to be learning about the octal and hexadecimal number systems. So you might be wondering, why do we need more number systems? Humans are really good with decimal, right? We have 10 fingers, so counting to 10 has kind of been a thing for us. Digital electronics understand binary. They understand zeros and ones, meaning like current meaning there's a 1, no current meaning there's a 0. Or voltage, right? Voltage is a 1, no voltage is a 0. Since computers have 32, 64, and 128-bit buses, those can be really big, long, annoying looking numbers like this. Kind of hard to for humans to see. And also, they're just longer, right? They will take more processing. But we can use hexadecimal, which is base 16, and octal, which is base 8, and we can actually represent binary data in a more compact form. And we're going to learn a shortcut by the end that makes it a little easier to convert back and forth between hexadecimal, octal, and base 2 binary. But what we have to do is we have to figure out how to relate all of these number systems to the one that we're used to, which is base 10. So we're going to review some of the binary stuff that we learned from before. If you remember back in the past, if we were converting from a decimal, which is the numbers we're used to binary, we would just successively divide by 2, and then each remainder would be one of our digits. The first one we get would be the least significant digit on the right, and then we would end up with, once we get nothing to divide by anymore, we stop. It's going to be a similar process with octal and hexadecimal. Instead of dividing by 2 every time with binary, to change it to octal, you'll divide by 8 every time. And for hexadecimal, you'll divide by 16. But it ends up being the same kind of process that we run over. And this is kind of what the counting looks like. We remember it was a big deal for us to learn how to count in binary because we use that in our truth tables. And now octal counting and hexadecimal counting. So once we get up to, for octal, we only need 8 individual numbers, 8 individual characters. So we just go 0 through 7. And then once we go past 7 to 8, now we have a 1 in the 8's place and a 0 in the 1's place. So for octal, in a decimal number, it was the 1s and then the 10s and then the 100s place and then the 1000s place. In binary, it was the 1s place and then the 2s and then the 4s and then the 8s and then the 16s and so on. For octal, it's going to be the 1s place, the 8s place, and then these are all powers, right? This is 10 to the 0, 10 to the 1, 10 to the 2. This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So this is 8 to the 0, 8 to the 1, 8 to the second power is 64. And then it would go on that way. And then hexadecimal, you'll have the 1s, the 16s, and then 16 squared is 256. So those would be your place values. So you notice that, so counting in hex, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F, and then 16 is a 1 in the 16's place and a 0 in the 1's place. So we're going to have to get used to identifying A as 10, B as 11, C is 12, D is 13, E is 14, and F is 15 for base 16. So this is from back in the day. To convert from decimal to base 2 binary, we just keep dividing by 2. And the first remainder you get is the least significant bit, and the last remainder you get is the most significant bit. And anytime you get a 0, then that's the last one you divide. That's the last number that you're gonna get. Going from binary back to base 10, we would just do multiply by the weights, right? The different the different place values. So for binary, it was the ones place, the twos place, the fours place, etc. And then you add them all up. We're going to follow the same pattern to go from decimal to any base and from any base to decimal. To go from decimal to any base, you're just going to divide by that number that the base is, and then go through the same process. To get from any base back to base 10, you're going to do the weighted addition. You're going to multiply the digit times that digit's value and then add them all up. And so we'll do some examples so that you make sense of these instructions. So here's an example of them. Here's an example of the process of going from decimal to base 8. So starting with 94 in base 10, we would just start dividing by 8. So we take 94, divide by 8. 8 goes into 94 11 times and has a remainder of 6, right? So 6 would be the least significant digit. So that one would go all the way to the right. Then you take the 11 that you got as your quotient, and now you're going to use that underneath. You're going to divide it. You're going to see how many times 8 goes into that. 8 goes into 11 just once. The remainder is 3, so our second digit is a 3. Then we're going to take the 1 up here. 8 goes into 1 0 times. Whenever you get the 0 up here, that means this is your last step. 8 goes into 1 0 times. The remainder is 1, so that's why our last digit here is a 1. So let's do one of these together. We're going to convert 189 from decimal into its octal equivalent. So we're going to take 189 and we're going to divide by 8 because we're trying to get into base 8. All right, 8 doesn't go into 1, but 8 goes into 18 twice. 2 times 8 is 16. So then subtract, you get a 2, bring down the 9. How many times does 8 go into 29? 8 times 3 is 24. So 3 times 8 would be 24. Subtract, and you get a remainder of 5. So that means that in base 8, I'll write it up here. In base 8, my last digit is going to be a 5. My least significant digit is a 5. Now I'm going to take the 23 and divide by 8. Well, I know 8 times 3 is 24, so it's going to have to be 2 times that it goes in. 2 times 8 is 16. So that's going to be a remainder of 7. So that means that my next digit, my next more significant digit is a 7. Now I have to take the 2. How many times does 8 go into 2? 0 times. And then your remainder is going to be 2 because 0 times 8 is 0. You subtract, you get a remainder of 2. So that means that the last digit we put is 2. So 275 in base 8. And then you can just see here, they show you 275 just without as much work shown. Okay, now to go from octal to decimal, we're going to use weighted multiplication. And so what we have is in the least significant place, that's the ones place. Then the next one over is the 8s, and the next one over is the 64s. And then if we had another digit, it would be whatever 8 to the 3rd power is. So then we take the digit in that place and multiply by the value of the place value, right? So 1 times 64 is 64. 3 times 8 is 24. 6 times 1 is 6. I don't know why it does that. Very strange. And then you just add those together. 64 plus 24 plus 6 equals 94 in base 10. Why does it do that? Okay, so let's do an example. We're going to convert 134 in octal to its decimal equivalent. So 134. The least significant digit is going to be the ones. So we're going to multiply that by 1. Then this is going to be the 8s, and then this will be the 64s. So we're just going to multiply and then add. 1 times 64, 3 times 8 is 24, 4 times 1 is 4. Add these together. This is 64 plus 24 is 88. 88 plus 4 is 92. So this would be 92 in base 10. Then you can see the way the authors wrote it on the next slide. So 134 in base 8 is 92 in base 10. Okay, so now let's look at hexadecimal. So to go from decimal to hex, now sometimes they'll call it hex just for short. Hex means 6 and decimal means 10. So 6 and 10 is 16. Sometimes you'll see them write like base 16 with a 16, and sometimes you'll see them write it with a capital H instead of the 16 down there. But we're just going to do dividing by 16. So 94 divided by 16. 16 goes into 94 5 times. 5 times 16 is 80. 94 minus 80 is 14. And then we have to remember that the hex version of 14 is the letter E. Just remember it starts at 10, right? 10, 11, 12, 13, 14, 15. 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So we have a remainder of 14 right here. So that means our first digit's going to be the E. Then when we divide, how many times does 16 go into 5? 0 times, remainder 5. So then that's the next digit. All right, let's do an example here. 429, we want to convert that from decimal into hexadecimal. So 429 divided by 16. I'm going to let my calculator help me out a little bit here. 429 divided by 16 is 26 point something. So I know that's going to be a 26 up here. So 26 times 16 is 416. So 416 will go down here, and the 26 will go up here. So 26 times 16 was 416, right? Yeah, 416. Okay, then we're going to subtract.
Sorry, where did we get 16 from?
Because we are going into hexadecimal, which is base 16. Whatever base you're trying to go into, that's what you divide by. So since we're going into base 16, we're just going to divide by 16. When we were doing the octal one, we were dividing by 8 over here. But good question, thank you. So 9 minus 6 is 3, 2 minus 1 is 1. So that's a remainder of 13. And then 13 was D, right? So I know my first digit in base 16 is going to be a D. My next step is going to take the 26 and do 16 goes into 26. That's only going to go in once. The remainder is 10, which is A. So then my next digit is going to be A. Now I need to take the 1 So 1, and then 16 goes into 1 0 times. The remainder is 1. So we get a 1 right here, and that's the last digit that we need to do. So to go from decimal into any base, you just do repeated division by whatever base it is you're trying to get into. And so you can see on this slide that for base 16, you can either write a 16 or you can write the H for hexadecimal. And other digital electronics engineers will know what you're talking about. Okay, so now let's go from hexadecimal back to decimal. And then we just have to remember that it's the ones place, then the 16s place, and then 16, if there's another digit, it's 16 squared, which is 256 place. And then you're just going to multiply the value of this character times the place value. So for this one, E is 14, so 14 times 1 is 14. 5 times 16 is 80, and then you add those together to get your decimal number. So let's take a look at an example where we do this. Let's take B2HE. I mean B2E in hex. And then let's see, B is 11. So let's think about this. What place are they? This is in the ones place. This is in the 16s place. And this is in the 256 place. So B was 11. So for this place value, I'm doing 11 times 256. For the 16s place, I'm doing 2 times 16. Erg, why does it do that? Doing 2 times 16. And then for the last one, I'm doing E times 1. E was 14, I think, right? Yeah. So 1 times 14. Now we're going to use a calculator. So 11 times 256 is 2,816. Then I'm going to add 2 times 16 is 32. So I'm going to do plus 32, and then I'm going to add 14. Plus 14, and I get 2,862. And that would be in base 10. And again, here's their solution, 2,682, perfect. Okay, now, how would we get from hexadecimal to octal? Right now, the only way we know how to do it, we know how to go from hex to base 10, and we know how to go from base 10 to base 8. So it'll be a two-step process. So we're gonna start by taking 5A in hexadecimal and converting that into base 10. Then we're gonna take that and convert it into base 8. All right, so to convert this hexadecimal number into base 10, we have to remember that this is the ones place and this is the 16s place. So we're going to be doing 5 times 16 plus A, which is 10 times 1. 5 times 16 is, that's 50, plus 30 is 80. So 80 plus 10 equals 90. So this is 90 in base 10. Then to go from base 10 to base 8, I just need to start dividing by 8 to get my digits. So I'm going to take 90, and I'm going to start dividing by 8. 8 goes in there once. 8 goes into 10 once. 1 times 8, we're going to have a remainder of 2. So my first digit is going to be a 2 in base 8. Now I'll take the 11, divide by 8 again. 8 goes into 11 once, and the remainder is 3. So my next digit is going to be a 3. Now I do the 1. 8 goes into 1 0 times, the remainder is 1, so our last digit we write is a 1. So we started with a number in hexadecimal. We used the weighted multiplication for the place values to convert it into base 10. And then we did the base 8 division over and over to get our digits for our base 8 octal number. Okay, but there is, wait, okay, now octal to binary. So, wait, did I miss the thing? No, octal to binary. So here's, we don't know how to go straight from octal to binary yet. So we're gonna have to go from octal to base 10. So we'll start in octal. Then we're gonna convert that into base 10. Then we're gonna convert that into binary, which is base 2. All right, so to convert into base 10, all we do is the weighted multiplication. This number is octal, so we have the ones place, then we have the eights place, and then we have the 64s place. So we're going to be doing 1 times 64 plus, we're going to do 3 times 8 plus, and 8 times 1. Okay, so we're doing 64 plus 24 plus 8. 64 plus 24 is 88. 88 plus 8 would be 96. So this is 96 in base 10. And then to transform or to change this base 10 into binary, we just are going to be dividing by 2 to get our digits. So I'm going to start with my 96. And we're going to divide by 2. Did I do that right? 20. Yeah, I think so. Oh, that's what I did wrong. I copied down the number wrong. I did 138 instead of 132. Let me fix it. That's supposed to be a 2, which means that's going to be a 2. That number is going to change. So this was supposed to be a 2. So I'm doing 2 times, this is a 2 here. This stays 3 times 8. So this stays 24, but this is just a 2. So that's not 96. That is 64 plus 24 is 88, plus 2 is 90. Okay, so now let me fix this up again so that it looks nicer. So this is 24 plus 2, the total is 90. And now we're going to start dividing by 2 to get our binary digits. So 2 goes into 90 45 times. 45 times 2 is 90, so the remainder is 0. So our first digit is going to be a 0. Then we do the 45. And you can kind of tell with binary, you can tell if it's even, the remainder is going to be, if the number inside here is even, the remainder is going to be 0. If the number inside here is odd, the remainder is going to be 1, right? But we still have to do it to figure out what number goes on top. So 2 goes into 4 twice, 2 times 2 is 4, then 5, 2 times 2 is 4, so we get a remainder is 1. So our second digit is a 1. Then we do the 22. 2 goes into 22 11 times, and the remainder is 0. So our next digit is a 0. Then we do the 11. 2 goes into 11 5 times. 5 times 2 is 10. The remainder is 1. So our next digit is a 1. Then we got to do the 5. 2 goes into 5 twice with a remainder of 1. So we're going to have another 1 there. Then we got to do the 2. 2 goes into 2 once. The remainder is 0. So we're going to have a 0. And then we have to do the 1. 2 goes into 1 0 times, and the remainder is 1. So the last digit we write is a 1. So that was kind of like a lot of work to get from 132 in base 8 to bind to its binary equivalent, right? We had to do the weighted multiplication, where hopefully we don't make mistakes writing down our work, change that into base 10, then we have to do the repeated division to get our base 2 binary. But there's a shortcut that we're going to learn in just a moment. Here is the shortcut. And notice that base 10 is not part of the shortcut, because base 2 and base 8 and base 16 are just powers of each other. 2 to the third power is 8. 2 to the fourth power is 16. So here's the shortcut. To go to octal, because 2 to the third power is 8, we're going to take them in groups of 3. We're just going to take the binary number and put it into groups of 3, and then say, well, what is this number in binary? 0, 1, 0, that is 2 in binary, right? Because it's the 1's place, this is the 2's place. So that's why we have a 2 right here. 0, 1, 1, that's a 3 in binary. So that's why we have the 3 here. And then if you have to do like leading zeros or invisible zeros, if you have leftovers, 0, 0, 1, that's just 1. And you can go in the other direction too. You could take your 132 base 8 and you could say, all right, well, what is binary for 2? It's 0, 1, 0. And then that goes there. What's binary for 3? 0, 1, 1. That one goes there. What's binary for 1? 0, 0, 1. That goes there. And then you can leave off the leading zeros if you want to. So to go between binary and octal, it's a 3-digit shortcut. You just group them into 3s and then translate them into binary. And to convert between binary and base 16, it's the fourth power, so we're going to take them in groups of 4. Then convert them into binary or convert them. And then if it's bigger than 10, then you do use a letter, right? So this one right here, this is a 2 and an 8. So this is 10, which is A. Here we have a 1 and that's the 2's place, that's a 4. So 4 plus 1 is 5. So let's go do a couple of examples where we use this technique. So we're going to convert the hexadecimal number A6. So that's in base 16. And we're going to convert that into binary and octal, right? So first we're going to turn it into base 2. I don't know how long it's going to be. I'll put the 2 over here. And then we're going to convert it also into base 8. Okay, so the shortcut says this is base 16. So I need to write 6 as a 4-digit binary number. So if you remember binary, it's the binary goes, it's the 1's place, the 4's place. No, it's the 2's place second. So this is 2 to the 0, 2 to the 1, 2 squared, so that'd be the 4's. And then the 8's place. So those are the 4 digits we're using, right? So we just need to look at, okay, to get a 6, we would do a 4 plus 2. So that would be 0, 1, 1, 0. So the 6 gets translated into 0, 1, 1, 0. And then the A is 10, right? So how would we get 10? We could do it by doing 8 plus 2. And that would be a 1, not a 4, a 2, not a 1. So 1, 0, 1, 0, that's 10, which is A. So then 1, 0, 1, 0, it would be get a 0 here, 1, 0, 1. So that is A6 in binary, right? This part here is the 6. This part here is the A. Okay, well now we want to switch that into octal. So what we're going to do now is we're going to take that binary number, 1, 0, 1, 0, 0, 1, 1, 0, and we are going to break it into groups of 3. And then since this one doesn't have a 0, we put like a fake 0 right here. Okay, so then what is 1, 1, 0 in binary? This is the 1's, this is the 2's, and this is the 4's. So 1, 1, 0 would be 6. 1, 0, 0 would be, that's a 4 plus nothing, so that's a 4. And then this one would be a 2. So in octal, that would be 246. So if you forgot, or if you thought it was okay to forget binary, you have to remember now that it was not okay. Then I think we have one more going in the other direction. I kind of already talked about this. You just group them into 4's or group them into 3's, depending on if it's hex or octal. Oh, it's weird. Oh, we already did that. Yeah, this is just showing us what we just did right there. And hey, that's the end of the lesson.